Okay, we're going to work problem 5.52 from the end of the chapter. This problem reads, there's a container, it's got a volume of 355 milliliters. It has 0.146 grams of neon that's been added into that container. Sometimes you might say the container or the vessel has been charged with 0.146 grams of neon. That just means it's been added. It's fancy chemistry language, right? And also we've added a small amount of a different gas here, so argon. So we're mixing the neon and the argon. Now we're not told how much argon we added. That's actually what we're going to be finding. But we do know the temperature of the flask is 35 degrees Celsius. The total pressure is 626 millimeters of mercury. How many moles of the argon must be present? Okay. Now the idea behind this problem is that the total pressure exerted by all gases in the sample is the sum of the partial pressures of the individual components. And another key idea to work this problem is that every gas, it doesn't matter if it's neon or argon, if it behaves as an ideal gas, it acts like an ideal gas. And that means that it's subject to this ideal gas law, the PV equals nRT relationship. It doesn't really matter what the gas is. All that's crucial for us is the number of moles of the material that's present. In other words, the number of moles of the total gas that's present defines the total pressure. Okay? So we're going to use this ideal gas law and work it a little bit to try to figure out how much argon must be present if these conditions are to be met. Okay? Based on what we know about ideal gas behavior. So let's work our way through this problem, adding variables that we know, seeing if we can find our unknown. Okay? And what do we know? First thing we're told, 355 milliliters is the volume of our container. We know that gases expand to fill their containers completely. I'm very confident as a result that I can list 0.355 liters as my volume V. Notice I converted directly from milliliters to liters by dividing by 1,000 here. I did that in a single step because I know that I ultimately want to use this 0.082 value from my R over here. And if I do so, I need to use liters for my volume and I need to use atmospheres for my pressure. Okay? I just always work these problems using liters, volume, and atmospheres, and I can remember this number in my head. It makes it a lot easier, okay? Just for me personally. Now, I need a P value, a pressure value, to go along with this volume. What do I know about the pressure? Well, I was told the total pressure is 626 millimeters of mercury. 626 millimeters of mercury. I just got through saying I needed to use atmospheres pressure, so I'm going to need to convert. But that's a pretty easy conversion by this point because I know there are 760 millimeters of mercury in an atmosphere. So those units cancel. I take 626 and I divide by 760, and that gets me my pressure in atmospheres. Let me see what I get if I do that. It looks like it's 0.8237 atmospheres. So 0.8237 goes right here from my P. And I've got my pressure in my volume. If I multiply P times V, I end up getting 0.2924 on the left-hand side of my equal sign. So now I go over to the right, and I think about it a little bit. Now, what do I know over here? Well, clearly I don't know the total number of moles. Now, I may be able to figure out how many moles of neon I've got because I know it's neon. I've got this many grams, so I just need to do a grams to moles conversion. But the thing is, in my container, I have argon mixed with neon. If I just solve for the number of moles of neon that's present and I plug that number here, I'm going to solve for basically I could solve for maybe the pressure exerted by the neon, say for instance. But the thing is that's not the total pressure because the argon which is present exerts some pressure itself. Okay, and I want to figure out what the total pressure is because this number is reflective of the sum of the partial pressures of argon and neon. So I need the total number of moles. So basically what I'm saying here, I think, is I need to add together two numbers. I need to add together NAR, which is the number of moles of argon, and to that I need to add the number of moles NE, which is the number of moles of neon. I multiply that sum times the R, the 0.082, and then I'm going to multiply that by T, my Kelvin temperature. Remember, whenever I have T's in these equations, must always be Kelvin temperatures. Extremely important. Now I'm given 35 degrees Celsius, but I know that my Kelvin temperature is just 273 plus 35. So if I'm doing the math on that, that works out to 308 Kelvin. And my 308 is going to eventually go right here for my temperature. So I made some progress here. My only thing is that I've got this one equation with these two unknowns, and I can't solve it for two unknowns with only one equation. But I know something else, okay? I was told in the problem the number of grams of neon. I had 0.146 gram neon in my container. I can look on the periodic table what the molar mass of neon is. And in fact, if I do that and I go to the periodic table and look for what it is 20.18 gram per mole. That then works out to 0.00723 mole of neon. So I was told in the problem I had this many grams, which corresponds to this many moles. So fortunately, I can then rewrite this equation. If I take the product of these two numbers, I get 25.256, that's just the 0.082 times the temperature. And I'm going to multiply that by NAR plus NNE, number of moles of neon. But instead of this variable, I'm going to plug in that number because I know that I've got 0.00723 moles of neon. That's my number of moles of neon. I was told that essentially in the problem. This makes things much nicer now because we only have one variable. It's the number of moles of argon that's present in our system. We can basically rearrange this equation now and solve for this. Now the way I'm going to choose to do that, I'm going to not do anything with this left side right now. Just bring down that number. I'm going to distribute this 25.256 across all of our variables. So 25.256 NAR times the number of moles of argon plus 25.256 times this number, which works out to be 0.1826 based on the notes. Okay, so we're just basically simplify that, just distribute that 25.256. Now the beauty of that is I can combine them my like terms. So I still got this 25.256 NAR, but that's going to be equal to 0.2924 minus 0.1826. Okay, so I'm just working the algebra at this point, and I can solve by dividing by both sides by 25.256. Okay, and that will be then equal to my NAR, which is the variable I'm looking for. And it looks like if you do the math on that, it equals 0.004347 moles. So that's how many moles of argon must be present in this container as a mixture with the neon to exert a total partial pressure of 0.8237 atmospheres when the volume is held at 355 milliliters at 308 degrees Kelvin. It's the only way the math works out. And again, the key concepts here are use of my ideal gas law, okay, but that's starting to get probably a little bit more familiar to you. I think what's a little bit tricky about this is this part right here, where we just add together the moles of each component. We're basically saying that each component exerts its own partial pressure. The two gases act and behave independently of one another, and both are ideal gases. Both follow this gas law, okay? If that's the case, you can do this mathematics and figure out how many moles of the second gas you got. So, fun problem.